Now, refreshing our memory on using the chain rule, actually using it, not reversing it, but using it when we've got a higher power of x in the brackets. We need to bring our power down the front, so we have 6. We also differentiate what's in the brackets, which in this case would be 2x, and we bring that out the front also. And then we rewrite what's in the brackets, reducing the power by 1. So tidying up here, you can see that we get 2 parts in our answer, and both of them are functions of x. There's x's out the front. And this is only going to happen if you've got x squared or x cubed or some higher power of x inside those brackets. Another one here, we've got x to the power of 4 plus 6. We bring the 3 down the front. We bring 4x cubed out the front as well. Then we rewrite what's in the brackets, reducing the power by 1. So again, we get an answer that's 2 functions of x multiplied by each other. Notice how if we've got x squared in the brackets, we get x out the front. We've taken 1 off the power. If we've got x to the power of 4 in the brackets, we end up with x cubed out the front. So a shortened version of this, when we've got some function raised to a power, we need to bring the power out the front. We need to differentiate f of x, bring that out the front too, and then rewrite our function, dropping the power down by 1. Now I know you know this already, but it's worth reviewing it now, because if we're going to reverse one of these types of chain rules, it's important that the thing that we try and integrate is going to have 2 parts to it. They're both going to need to be functions of x, but more importantly, the function of x that's out the front of the brackets is going to need to be with a power of x that's 1 smaller than what's in the brackets. If it's not, we're not going to be able to reverse the chain rule. So we can only do it under quite specific circumstances if we're given something that's doable. So then the easiest questions to do of this more difficult type would be if we were given something to integrate that had 3 parts. If we had n, this is just a constant, and we had some function raised to a number that was just a little bit smaller than that, and we had the derivative of that function also out the front, we could really easily integrate that just to get something super simple, that same function raised to the power of n. Now how do we know this? Well, let's differentiate this and show that it gets that. If you differentiate a function raised to the power of n, you bring the n out the front, you also bring out the differentiation of what's in the brackets, raised to the power of n, whoops, there's no brackets there, and then you take that same function but you don't raise it to the power of n, you drop the power down to n minus 1. So we already know that this works, and we can work backwards to say we'd like to integrate this because it will give us something really simple. But here's the thing, when we're looking at something that we want to integrate, we don't know what this part is. So it makes sense for this to look nice and simple with numbers like n in there. And having this n minus 1 makes things a little bit tricky to think through. So I can rewrite this formula by swapping n for n plus 1. So that way when I'm looking at something that I am asked to integrate, I can see what the power is and just call that n. Then I'd be hoping in an ideal world to have a number just a little bit bigger, n plus 1 at the front, and then f dash x, and then f of x raised to that power, because I know what to do with that. It would just be the function raised to a power just a little bit bigger, and that would be the same as the one at the front. This would be ideal, 3 parts. But wait, we don't always need this part, do we? This constant out the front. Think about things we've already learned to differentiate really simply and easily. Ideally, it would be nice if we're integrating something raised to a power if that n plus 1 was out the front, because then we could just do this. Let me give you an example. If we were integrating 3x squared, it would be so easy to say, hey, that's going to give us x cubed. Notice how the 3, when we differentiate x cubed, comes out the front and we drop the 3 down to a 2. This differentiates perfectly to that, so if we're given that, we go straight to something that's super simple. But don't forget that we've already learned how to deal with there not being a 3 there. We know that if we're going to integrate something like x squared, we raise the power by 1, and we divide by the new power, and that makes up for the fact that we weren't given that constant out the front that in an ideal world would be there. So we already know how to account for this. And the rule says, of course, if we're integrating x to the power of n, we can raise the power by 1 and divide by the new power. So that gets us around that problem of not having that extra part at the front. So the best version of our formula for reversing the chain rule would be this one. because it only relies on being given 2 bits, not 3. And we account for this constant not being quite right by just dividing by the new power. So then what we want, though, to be able to reverse the chain rule, we need the function that's raised to some power n to have f dash x, in other words, the differentiation of that function, out the front of the brackets. And if we've got that, or we've got a multiple of it, and we can adjust it slightly, then we can work with it. What do? Well, we just raise the function to a power slightly bigger, n plus 1, divide by the new power, and of course we can see that differentiating this would give us that. Let's just double check. If we differentiate this, the n plus 1 would come down the front but instantly cancel with this n plus 1, they both disappear. And we'd have to drop the power down from n plus 1 to n, which is what we have, and we'd have to differentiate what's in the brackets and get f dash x and bring that out the front, and that's exactly what we'd have. So we can see that this formula works. Now let's have a look at how we can use it.